thank you very much again for everybody being here, and for those that are logged in remotely in another session of the QRC seminar. This is again a nice session that we have the speaker in person here with us. We have Professor Professor Antonio Acín from ICFO, Barcelona. He's the director of the Quantum Information Theory group there. It's in fact one of the largest quantum information groups in Europe. And Professor Acín is an authority in our field. I didn't prepare any official bio, so I'm going to improvise with what comes to my mind, right? So Professor Acín, well, he's written many papers about quantum information. He has been awarded the ERC grants like 2 or 3 times, starting grant, consolidator grant, advanced grant, and also some AXA prize, if I'm not mistaken, right? Professor Acín is one of those guys that understands theory, and he also has a background in engineering. So he's not been just writing papers on theory. He has a long story of collaborations with experimentalists, also at least in the photonic side. And this is also very special for me because I spent 4 years as a postdoc. I did essentially a second PhD with Professor Acín in Barcelona. I spent 4.5 years as postdoc there. And it's really a great pleasure to have him here. He did a big effort for coming. He's here just for 2 days. So he flew overnight tonight, and then he will flew overnight again on Tuesday night or so, tomorrow night, right? So he'll be here just today and tomorrow. So take advantage to if you want to discuss with him. He's going to be free tomorrow, essentially. And yeah, it's a pleasure to have you here, right? So please proceed. Thank you for coming.
Yeah, well, thank you very much, Leandro. I mean, for this very nice introduction. Well, as you can understand from the introduction, Leandro was my postdoc, but we also became friends during the 4 years. Okay, that's why he's saying so many nice things about me, and I thank him for that. Yeah, so it's very nice to be here. I wanted to stay longer, but okay, I mean, there were some complications, and so I had to be here for 2 days. But if you want to discuss with me about anything, just drop me a line, and we can try to look for a discussion room that is free. I mean, I already understood that this is an issue at the moment, but yeah, I mean, whenever you want to discuss with me, just let me know, and we will see what we can do. So when I was invited to come here, I was thinking about what to explain, and in the end, I opted for, say, a conservative talk. So I will tell you about, say, one of the main things in my group that has been historically, because I assume that maybe this is the most suitable topic for a general audience, let's say. But yeah, I mean, if you want to know about any of the latest developments, just let me know. Okay, so the topic of my talk is about certification of quantum technologies. So if you look at the latest ERC advanced grant I got, it's called Certification of Quantum Technologies. So this is, I mean, this ERC is an important grant we get in Europe, and somehow you define the research for the next 5 years. And my research, I mean, one of the main themes will be on certification of quantum technologies. Okay, so, well, this you all know, no? This is what the field is about, quantum information theory, technology, science. I mean, you want to understand what happens when you encode information on quantum particles, and what we know is that new things happen simply because the physics is different, okay? So, and I think whenever I give talks to a general audience, perhaps you are already aware of what I'm going to say, but I think this is something that it's really a change of paradigm, at least it was for me, okay? So I studied engineering and physics, and at my time, there was no course on information theory in physics. Okay, all the information theory I learned from engineering. Okay, not much, I must say, and this is because information was thought to be something independent of physics. Okay, this was somehow the main thing about information. No, I mean, you could talk about bits without making any reference to physics. Okay, any physical system that could take 2 values was, from a logical perspective, equally valid to encode a bit, okay? But somehow with quantum information theory, we understood that this is not at all true, okay? So it matters whether you encode the bit on a particle described by classical physics or on a particle described by quantum physics. So physics matters a lot, okay? I think this is something, whatever quantum information science will bring us, this is something will remain, okay? So, okay, but now what happens if physics matters? Well, then you have to really understand the physics of your devices to understand what they are giving you, no? And then what is happening now with quantum information technologies is that it's a very exciting moment where we have first commercial products that arrive to the market. Well, in the case of cryptography and random number generators, it's already some years that we have products, no? And then, okay, we have, say, quantum computers, quantum computing devices, okay, devices that are assumed to solve a problem, computational problem using quantum physics. Then we have quantum simulators, which are devices that simulate some other systems of interest. Then we have prototypes that you can use to secure your private information exchanges through quantum cryptography, or you also have some other products that generate randomness according to quantum physics. Okay, so, and what is happening now is that you want to buy these devices and you go to the provider and you say, okay, please give me a quantum computer. And then the quantum provider does, okay, here's the quantum computer. And it gives you a device, okay? And then you look at it and say, is this a quantum computer? And the provider will tell you, yes, okay? And you pay a lot for that. Okay, so I think there is now, we need to have tools to certify that this is really a quantum computer, a proper quantum simulator, this is cryptographically secure, and this is quantum random. And this is somehow this is what my talk is going to be about. This is certification. Okay, so you are going to be given a device and you have to certify that it has a correct functioning. So it's a relevant, say, in my opinion, applied problem. It's very transversal to quantum information. You see here, I'm putting many quantum information applications and it affects all of them. And it's also, if you think about, from the point of view of science and technology, it's technologically relevant, but it's also scientifically relevant, okay? Because the problem with certification is that at the moment, we don't have many quantum devices. So we have to certify quantum devices with our poor and limited classical information devices. Okay, so we have to face, actually, the problem we have to face is the one that gives the quantum advantage. Okay, so we have quantum advantages because we cannot replicate quantum devices with classical devices, but then we have to use these classical devices to certify at the moment these quantum devices. Okay, so there is a problem there. And also, if you want to certify that something is quantum, okay, you have to understand what are the properties in which quantum physics departs from classical physics, because these are the really properties that are useful to certify quantum devices. So it also goes at a very fundamental problem of where quantum physics differs from classical physics. And this type of certification is especially relevant if you think about, if you are paranoid and you care about cryptography. Okay, so again, when you work in quantum cryptography, you have to assume that the worst can happen. Okay, you have to really be paranoid. Okay, so trust is an issue. Okay, so if you want to secure cryptography, you go to a provider and tell you, can you please give me, I want to exchange a message with Leandro, and we go and buy quantum cryptography. And again, we go to the provider says, here you have quantum encrypted solutions. And then it's just a box. Okay. And this is precisely what happened. This is behind what happened in the hacking attacks that we had some years ago. I don't know if you know this, but so in principle, quantum cryptography, like a protocol, the historical protocol like BB84, it's assumed to be secure. So there is a security proof. Some mathematicians found a security proof, and they tell you, okay, if you use this protocol, no one can hack your information transmission. Well, then several teams, in particular, Makarov and co-workers, here's a picture of Makarov, they went to one of these companies selling these devices and they hacked. Okay, and then it was like, how can it be? Someone is lying or something is happening here, okay, because there is a security proof for that, okay? So there was something that we didn't understand at that time, okay, because someone was hacking a protocol for which there was a security proof. Okay, and okay, so now if you think about it, there might be several possibilities for that, okay? So one possibility is like Makarov and co-workers found a mistake in the mathematical security proof, okay? But he doesn't look like a mathematician, okay? He's in the lab with many devices. He's not a mathematician. He's an experimental physicist. The second thing is that usually BB84 is explained to be secure because based on the laws of quantum physics. Maybe Makarov hacked the laws of quantum physics. Well, he would have got the Nobel Prize for that, okay? This is not what he did, okay? So there was something that we didn't understand. And this is what they did, okay? So they broke the implementation, but not the principle. And by this, I mean the following, okay? So if you look at BB84, for instance, I'm assuming you all know what BB84 is, okay? But if not, it's not so important, okay? So in BB84, when you read the protocol, it tells you you have to prepare spin-1 qubit states pointing in the Z and X direction. Alice has to prepare this state, and she has to send these states to Bob, who has to make measurement in the sigma X and sigma Z basis. And you make the key out of that. Okay, so this is what the theory demands. Okay, you have to prepare these objects living in a Hilbert space of dimension 2. You have to make these measurements, and then you have a security proof. Very nice. But now let's think about what the provider does. Okay, I mean, does the provider prepare states living in a Hilbert space of dimension 2? Well, this is impossible by definition. Okay, so just think, what do people usually do? For instance, a standard scenario is that you put something in the polarization of a photon, but a photon is not an object that lives in a Hilbert space of dimension 2. It has a frequency, orbital angular momentum. It has many degrees of freedom. Actually, any particle has infinite degrees of freedom. So certifying that this is happening, it's impossible. So the provider will tell you, like, well, I don't know how to prepare these things. Do you mind if I use a laser source for that? Well, for sure, a laser source is not something that lives in a Hilbert space of dimension 2, okay? And then you say, like, okay, I don't know how to make Stenger-like ideal measurements. Do you mind if I use a single photon detector? Well, for sure, a single photon detector is not an ideal Stenger-like measurement, okay? So this is where we theorists find our results. This is where we establish the security proof. And this is what the provider experimentalists do, okay? They do things with attenuated laser sources and with single photon detectors. So you have a security proof here under these assumptions, but this security proof, in a way, is irrelevant for your implementation, okay? Because the security proof is based on some assumptions that are impossible to certify in practice. So even if the provider tries very hard, it's really, there is no way you can certify that something lives in a Hilbert space of dimension 2. So then what the Makarov and co-workers did, they hacked the implementation, even if there was a security proof for the theoretical description of the protocol, because there is a mismatch here. Okay, so here there is something that I think also we learn from these attacks, okay? Physics matters, but if physics matters a lot, then this might be a weakness for your devices, okay? So if you, especially in situations in which you fight against an enemy, if the security, say, of your protocol depends a lot on many details of your physical realization, this might be a problem, because you should better meet these details in the implementation. Otherwise, what you prove in theory does not apply in practice. And this is related to another problem which is relevant for cryptography in general, which is the problem of certification. Okay, so and trust. Okay, in cryptographic applications, you always put trust on the provider. Okay, you go and say, like, can I have a QKD quantum cryptography solution? Sure, and you get a box. Okay, and you put trust on the provider. Okay, so, and it would be nice to remove this or minimize this level of trust, because the fewer the assumptions you have to make on your devices, or the trust you have to put on your devices, the stronger the security. So I always use this example that was became evident with the Snowden affair. So it was like there was a cryptography solution that was promoted by NSA. Okay, so it was saying, NSA was telling people, like, please use this cryptographic solution. Okay, if NSA tells you that you should use a cryptographic solution, maybe you think twice about it. Okay, but the problem is that NIST, the National Institute of Standards and Technology, say that this was a good solution. So NIST, I mean, they are made to provide trust. Okay, this is what they have to do. So people use that, but then in the Snowden affairs, it became clear that this was not secure, even if NIST had certified the solution. Okay, so they say, like, no, stop using this. Okay, so you were using this solution for which you said there was trust, you were trusting the solution, but it was not secure. Okay, so it would be nice to remove the amount of trust and that you need for that. Okay, and okay, that's in my talks. I always use this joke. I'm always hesitating about removing it because I've used it many times, but I think it's perfect to describe what I want to say. Okay, so imagine you want to buy a random number generator and you come to me, and then I tell you, like, yes, here's my random number generator. Okay, so this is you and this is me, and this is the random number generator I'm selling to you. Well, I mean, how do you know that this is random? Okay, I mean, how from the outside, okay? And as you know, the probability that a proper random number generator generates this sequence is the same as any other sequence, okay? And the situation is even worse if you come to me and then I say like, sure, I have random number generators, but I even have quantum random number generators, and I charge you twice for that. But for you, I mean, this is one box and this is another box, and I put a Q maybe in one, okay? So, well, this is what I can do that, okay? So this is the problem we want to solve, okay? So how can you certify the presence of quantum randomness from the outside, or more in general, how can you certify quantum devices from the outputs they produce, okay? So this is a problem. This is what you get from the provider, a box or a device, and this device does something. But you're never going to open the device and see, here I see my qubits that are being prepared and these gates have been implemented. Okay, for that, one of our main obsessions is what is called the device-independent scenario. Okay, so this is a language that we have been using. I mean, we are working on that. Some other groups are working on this field or subfield of quantum information theory, in which you try somehow to get as close as possible to the scenario I'm describing to you. Okay, so if you go to a provider and you buy a quantum information device, you get a box. And if you want to certify the device as a poor user, you have to certify the device from the statistics it produces without opening the box and seeing what's going on. So we want to do a quantum information theory for black boxes. Okay, so, and we want to run with these black boxes quantum information protocols. And if we achieve something with these black boxes, and we can guarantee that these black boxes behave in a given way from the statistics they produce, then there is no mismatch between the theory and the implementation. Okay, because all what we do is based on the statistics that the devices generate. If I see the statistics, the devices behave correctly. If not, I give them back to the provider. Okay, so this is the main why we introduce this sort of quantum information theory with black boxes. So I have to give some structure to these black boxes, otherwise I'm not able to, I mean, it's very hard to make theory and prove things with boxes. Okay, so I have to provide some mathematical formalization of what I plan to do. Okay, so this is what I'm going to do. So I will assume that in this I can interact with these boxes. They might be quantum, but I'm going to interact with the boxes classically. So I can provide a classical input on these boxes, and then they generate a classical output. There might be something quantum here producing the output given the input, but this is the way we interact. Okay, because this is the way we interact with devices. Okay. So if you want to think about how we interact with the boxes, you can think that the device you get from your provider has n buttons, okay? And you can press button 1, button 2, button 3, button 4. Which button you press is given by this index here that can take n values. What the box does when you press button 1, you don't know. You're never going to open the box, okay? But you can have n different actions on your device. Okay, I mean, button maybe is not the most convenient way of doing this. Okay, you're not going to spend time pressing buttons. Okay, but you should think that you can provide a classical symbol that can take n possible values. And then as a result of this action, the box gives you a result. So you can think as if the box had at the bottom r possible lights, and whenever you press one button, one of the lights is on. Okay, but this is just a way of seeing that. I mean, it can be a knob that you can put in different positions. It can be that the box, depending on the node, gives you a node. Okay, it's irrelevant. These are just labels that I put. And what I describe, the way I describe the devices is just by the statistics they produce. So what is the probability of seeing output A1 here, AI, AN, when I use input X1, XI, XN? Okay, this is what I'm going to use to describe my boxes. Is this a qubit, a q-treat, a q-quark, a q-fifth? I don't know, and I don't want to make any assumption of that. Here, there is a quantum process producing the output given the input. Well, I mean, you can interrupt me anytime, I believe, no? Yes. But it's fine if you don't do it. Okay. So how can I do this? I mean, if you think this scenario is very minimalistic, okay? How can I do things in this scenario? Why can I do things in this scenario with these boxes? Okay. Okay, so this is another of the take-home messages I want to give you, okay? Because I like very much what's going on here, okay? So the interesting thing is that the statistics that I'm going to call the correlations between the devices depend a lot on the physical theory that you use to describe these devices. Okay, so this is going to matter. So I'm going to deal with physical correlations. But before proving that, let me just tell you what I mean by this correlation. Okay, what is the statistics? Okay, and I will do it for the simplest scenario in which there are two devices, one with Alice and Bob, and they can have n inputs and r possible results. So what is this object I'm talking about? Well, this is the object they see. Okay, so Alice and Bob, they spend some time pressing button 1, 1, say, and they see with probability P11, they see the output 1 here and 1 here when they use input 1 and 1. This is a probability. Sometimes they will see output 1 here, 2 there, when they press button 1 and 1, or they use input 1 and 1. And so on for the same combination of inputs. Clearly, these are probabilities, they are positive, and they sum up to 1. Okay, this is standard probability theory. I'm not doing anything. Okay, so for the same combination of inputs, you see the probabilities of all the outputs. Of course, you will have a similar vector for the case in which you use input 1 here and input 2 here, no? Positive numbers summing up to 1, and so on, so on. So this will be, I mean, I put it as a matrix, but it will be a vector, if you want, of m squared, r squared positive numbers that sum up to 1 in this configuration. This is what I call correlation. This is mathematics at the moment. Okay, let me just give an example, okay? So imagine you have this situation. I'm going to take the situation in which they make two measurements that I call 0 and 1. I can call it 1 and 2. I can call these measurements yellow and green, okay? So it's just label. I'm going to use this label now, 0 and 1. And the output, I'm going to call them plus and minus 1. I can also call them 1, 2, Leandro and Tony, okay? So these are just labels, okay? The only thing that matters are the probabilities. So let me just take the situation in which whenever they use the input 0, 0, okay, they see plus, plus, okay, this probability is half, or they see minus, minus. Okay, this is like sort of measuring a singlet, okay? When you make a measurement in the singlet, you see either plus, plus, or minus, minus. Okay, and of course, these two numbers have to be 0. Okay, I'm inventing this, okay, for you. I mean, I'm not talking about any theory. And let's imagine also that the same happens when they use 0 and 1. The same happens when they measure 1 and 0. But when they measure 1 and 1, they only see minus, plus, and minus, minus, and minus, plus, or plus, minus. Okay? Do you see anything fundamentally wrong in this table? Okay, this could happen, no? You could go here, you have experimental labs, no? It could happen that you prepare a system of two particles, you make two measurements, and you see when you make measurement 1 and 1, you see only plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, 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 plus, minus, plus, minus. Okay, I'm just inventing. So up to now, I didn't give any, it's just mathematics. You can here put any positive number summing up to 1. Okay, but I'm a physicist, and I guess many of you are. So this is what I was telling you. Okay, so now let's think that these are not arbitrary devices, they are physical devices. And this is what you should also remember from my talk. Okay, so physical principles give you limits on correlations, give you limits, give you structure to this vector of probabilities that you can think of. So first thing, in all my talk, I'm going to assume that what is happening in this process, there is no communication. Okay, so I can think of these two as two separate devices. Okay, for me, if you draw two different devices and you assume that they communicate, two communicating devices for me are not two devices, it's just a single device. Okay, well, it's a bit of terminology, but if you tell me that you have two devices, the devices don't communicate. Anyway, I'm going to assume that they don't communicate. Okay, so you give the input and you produce the output. There is no communication from this device to the other one. Okay, so this is telling that you can define a marginal probability for this device. Okay, what this device sees, the probability of the output given the input, does not depend on the other device. Okay, this is called non-signaling correlations. You can think in the most, say, paranoid case, you can enforce these constraints by arranging the devices so that they define space-like separated events. So there is no time for light to go from one device to another. Clearly, this is telling you that this device statistics cannot depend on what the other party does. Okay, because if it was the case, you could signal faster than light. Okay, because you here, by doing something on your device, could modify the physics of my device. We believe in special relativity. This is not possible. Okay, so this is why I'm imposing a physical theory, and this gives me a constraint. In general, this is telling me that the marginal probability of a subset of the devices does not depend on the input of the other devices. Okay, so let me go back to this situation, this table I was showing for you. Okay, so what I'm demanding here is that the probability that this party sees +1 when she uses input 0, well, this is the probability that she sees that both parties see ++ or +-. You see, I sum over the second party result, plus and minus. Okay, so this is the probability of seeing that one party sees +1. This 1/2. Here I'm assuming that the second party measures 0, but this has to be the same when the second party measures 1. Okay, because if it was not the case, this party, by measuring 0 and 1, he could change the probability that this party sees +1 when she measures 0. Okay, this is not signaling constraint. It's very simple. So I only have to sum this plus this has to be equal to this. Okay, so these are just linear constraints, very simple to understand. But this is happening here, and in fact, if you check all these non-signaling constraints, you will see that nothing is violated. Okay, so if you see this, if you make an experiment and you see this table of probabilities, you are not violating special relativity. Good. Okay, so. Okay, so this is a set. Okay, so you now see that the numbers that I can put in this table are not arbitrary, depend on special relativity. Now, before the advent of quantum physics, what are the possible numbers you can expect? What are the possible correlations you can expect? Well, if these devices are prepared by a provider, no, and they give these devices, one to Leandro, one to me, or we share all devices here. Before quantum physics, the way we reasoned about correlations was the following. So the provider wrote some instructions in the devices. You can think of these instructions as a small daemon sitting in the device. And then the daemon was getting the input and producing the output in a deterministic way. Okay, so this is the daemon is what I call lambda. The daemon may change the behavior with a given probability, produces the output given the input and what is inside the device. Well, this is if you know about foundations, these are the EPR local hidden variable models. Okay, so this is what I'm going to call classical correlations. Well, not all assignments of numbers here can be described in this form. And as you possibly know, we have quantum correlations. What is quantum correlations? Well, some statistics is quantum whenever there exists a Hilbert space in which I can define a state, some measurements for the first device, some other measurements for the tensor device. I put a tensor product because they are separated device. I take the Born rule, I combine them, and I get these numbers. This is what I'm going to call quantum correlations. Are these qubit Q3 correlations? No. Okay, some correlations are quantum whenever there exists a Hilbert space in a given dimension in which I can find these objects, combine them, and give me these numbers. So what we know is that these sets, I mean, now you can see this as this vector of probabilities define some sets, okay? Some of them are classical, some of them are quantum, some of them are no signaling, and we know that these sets are strictly included, okay? So the set of classical correlation is strictly smaller than the set of quantum correlations, which in turn is strictly smaller than this set of correlations that satisfy special relativity. Okay, this is Bell's theorem. And this was proven by Tzielson, Popescu, and Rorley. Okay, we have some points here that do not violate special relativity, but they are not quantum. Okay, for that, to prove this thing, to tell you about these things, I'm going to use Bell inequalities. Does everyone know what a Bell inequality is? Is there anyone who doesn't know? Okay. I will give a super quick course on Bell inequality because it's something very simple, so you can understand. So what is a Bell inequality? It's just the same scenario I was describing to you. Okay, so there is you make an experiment in which you prepare a state of two particles. I give it in physical terms, but you can think of this as the previous provider that sells you the quantum information devices. If the provider sells you two devices, or the source produces two particles, you make two measurements of two outputs, or you press two buttons giving two lights, it's the same language. Okay, and now you construct this expression that you can compute from the statistics. Okay, so this is the output of the first device when you measure input 1, and this is the output of the second device when you measure input 1. Okay, and this is the output of the second device when you use input 2. So it can be plus and minus 1. So what is the value of this quantity in classical physics? Well, this is plus and minus 1. So if I put here plus and minus 1s, it's easy to see that this is bounded by 2. Okay, well, maybe you have seen this, but it's so simple that I can do it again. Okay, so I'm not going to make the proof. It's very simple, but I don't know, if every device says plus 1, you can see that the value of this quantity is 2. Okay, because you have plus 1, plus 1, plus 1, minus plus 1, 2. This is very trivial mathematics. Well, this is a Bell inequality. Okay, so it's an inequality satisfied by all situations in which these outputs are predetermined, as in classical physics. Well, the beauty is that you can violate this Bell inequality in quantum physics. Okay, so if you prepare this state and you make these measurements, the previous expression is equal to 2 square root of 2. Okay, so I always want to explain this because I find it amazing that this is violated. Okay, so we don't have ways of producing a quantum Bell inequality violation now here, but if we had, I'm sure we could go to a layman in the streets explaining the rule of the game and say, okay, how much you are willing to bet for me to get a value larger than 2? Okay, I'm sure people are going to, because the rules are very clear. Huh? You write this and you can easily prove that this is bounded by 2. I'm sure you will find people betting. Okay. So if we had singlets here, we could go, Leandro and I, with our singlets, okay, and then take the singlet, making a measurement and producing the output and violating the Bell inequality and getting a lot of money. This would be the first application of quantum information technologies. Okay. So, well, this is just telling you that quantum correlations are different. Okay. So this is a Bell inequality. It's just a separation between the classical world and quantum correlations. This is telling you, you see, a Bell inequality is like a hyperplane, and the only thing you vary is this term, but not the slope. Okay, so this hyperplane varies. It's equal to 2 for classical correlations, and it's equal to 2 square root of 2, and this is the maximum, was proven by Silson. Now, if you had this table of probabilities I was showing to you before, you could violate CHSH up to 4. Okay, so what is this telling you? This is telling you that if you go to the lab, you make an experiment of 2 measurements of 2 outputs, and you see these probabilities, you are falsifying quantum physics in the same way as a Bell inequality violation falsifies classical physics. Okay, so if you find these probabilities, you should better double check. Okay, because. Okay, so if now, let me just sum up what I'm saying. We want to make protocols, quantum information protocols with black boxes. For that, I need to explain the statistics, and I need to use statistics that are intrinsically quantum. So what I have to use are these points here. Okay, because if I'm using these points, I know that my devices are quantum because there is no classical way of producing the statistics here with classical devices. So I should have, if I want to do this, I should have a good knowledge about this region here, because this is the region I'm going to use to make protocols. I'm going very slow. This is what we did in a paper. Okay, so it doesn't really matter. Okay, huh?
That's great.
It's great that.
It's going well.
Oh, okay, well. So what we did is we solved the previous problem. Okay, so if I give you this point, is this quantum? Okay, you see, this is a very innocent question. Is this? Does this impossible for quantum physics? It doesn't look like, no. It's just halves and zeros. But there is no way you cannot find any state in any Hilbert space and measurements for Alice and Bob that when you combine it with the Born rule gives you these numbers. It's impossible. This is why you would be falsifying quantum physics in the same way as Bell inequalities falsify classical physics. For this case, we know that this is not quantum because Siverson proved that this is bounded by 2 square root of 2, and this gives you 4. But what if I give you some other numbers? What if I give you these numbers? Is this quantum or not? Can you go to the lab, prepare 2 particles in dimension 10, make 2 measurements of 2 output and get these numbers? Who knows the solution for that? I mean, it's crazy, no? That and what you can do is like, I'm going to try with qubits. And then you don't find any qubit state and measurements giving you this number. Does this mean that this is not quantum? No, maybe you can do it with Q-trees. Then you have to run dimension 3. You don't find any realization. Does it mean that it's not quantum? No, maybe it's dimension 4. So to answer this question, you have to explore all possible quantum explanations, all possible Hilbert spaces. This is why the question is challenging. So what we did, it's already 15 years ago, we found a way of approaching this problem. So what I want to know is whether some points are quantum. What we did, we gave outer approximations to the quantum set. So you run this test. If the point is within one of these sets, it might be quantum. But if the point is outside one of these sets, for sure it's not quantum. Okay, so we can falsify quantum points, non-quantum points. So, okay, this is very speculative, but we have tools to falsify quantum physics in the same way as a Bell inequality falsifies classical physics. But this gives us way also to have a good understanding of what is possible with quantum physics, which is what we need for this device independent. Okay, so this is not quantum. Okay, so again, if you go to the lab and you see the statistics, you should better double check. Okay, so we have the tools to characterize quantum correlations. Now let's do protocols. So let's do a protocol for randomness. I always explain this with sort of a bit tricky example. I mean, okay, imagine you have a virtual casino and you want to buy a random number generator. You want to start a business with a web page, okay, with a virtual casino. You come to me. And I know that you have a virtual casino. So what I do, and I have quantum technologies. So I have a very good quantum random number generator. Before you come to me, I generate many random numbers. I copy these random numbers in a classical memory. I put this classical memory into a box. I paint it in fancy colors. I write quantum random number generator, and I charge you a lot of money for that. So you say like, is this a quantum random number generator? I tell you, yes. Okay, but okay, you know, I'm Spanish. You shouldn't trust Latin people. So you say like, I want to double check what this guy told me. Okay, so you take your quantum random number generator and you start generating random numbers, and you try to see with this, you know, random numbers, the quality of random numbers is tested with statistical tests. Okay, so you start generating random numbers and they pass statistical tests. I'm assuming that the size of the memory is very large. Okay, you say, Antonio Acín, nice guy. I'm going to use this for my virtual casino. Well, the numbers are random to you, but of course they are not random to me. I generated them. I get all your money. Okay, because what the test you have, they don't guarantee the randomness you need for your virtual casino. But now you have followed what I'm saying, okay? So you say like, no, we have to do something different. So we have to make sure that the origin of the random numbers is quantum. And what is the difference between classical and quantum physics? The violation of a Bell inequality. Because you want to certify things from the statistics. And the only way of producing statistics that is not classical is through a violation of Bell inequality. If you add assumptions about the boxes, you can do some other classical quantum separations. But from the statistics, there is only a way of certifying quantumness, which is through Bell inequality. So you have to come to me, and you have to ask me 2 devices that violate a Bell inequality. And you have to use these outputs for your virtual casino. Because if a Bell inequality is violated, the observables cannot have well-defined values. Because if they had well-defined values, the Bell inequality wouldn't be violated. So the Bell inequality violation is a stamp, a certification of the quantum randomness of your numbers. So now you should take the numbers produced by a Bell experiment, use them for your virtual casino, and there is no way I will get your money. So using what I'm telling you, we can generate these curves, okay? So from the CHSH Bell violation, from 2 to 2 square root of 2, we can bound the predictability on the output. Okay, so you generate a 2 output measurement. So you can go from 1 full predictability to half no predictability. And from the Bell equality violation, you can get this predictability. And for that, we use this method to bound quantum correlation that I was telling you. Okay, I don't have time to tell you, okay, but we have tools to quantify the randomness produced in a Bell experiment without making in a black box approach. But in a Bell experiment, you have randomness here, but this randomness is correlated to the other output, okay? It's correlated, okay? It's not local randomness, it's correlated randomness. I don't have time, but correlated randomness is almost a secret key. Okay, a secret key is something in which Leandro and I, we have random bits, but whenever I have a 0, he has a 0. Whenever I have a 1, he has a 1. So the same idea can be used to make cryptography device independent. I don't have time, but believe me. Okay. And now that the last thing, I'm hurry up a bit now, but the last thing I wanted to tell you is about some of these ideas can be used also in a quantum computation perspective. Okay, this is, I mean, randomness and device independent QKD, this is much more established. Now I'm going to tell you something in which we know a bit less. So what we have in mind here is like, okay, we have some devices that give you a solution to a computational problem, and now I'm going to focus on ground state problems. Okay, this is a very standard problem in which you can encode computational problems, but also simulate in a very popular use of quantum simulations. If you want to simulate the physics of an interacting problem, many-body problem, and you want to find the ground state. Okay, so what all these devices do, they are physical devices, okay? So they give you, with variational methods, with cooling down system, it's always a physical state that gives you an approximation to the ground state. So by definition, this gives you an upper bound to the ground state energy. Maybe the ground state energy, okay? I don't know, but it's always an upper bound. So we would like to see if there are ways of, okay, is the output of this, is this upper bound good? How far is it from the true values? Okay, so you can think of this, assume this is the ground state energy of my system, okay? And then you cool down or you do a variational answers. I mean, are you here or here? We don't know, okay? How good is your approximation to the ground state energy? So we would like to find ways of having an idea about this, okay? So what do you need then? Well, if this is the ground state energy, what you need is a lower bound to the ground state energy. Okay, because you have a lower bound and you take the upper bound, you can still have some control about the energy gap in which your solution is. Okay, so what do you do for that? Well, I don't have time. But basically the idea is similar to what I was telling you before, okay? So what is the minimization problem you want to find? You want to find the ground state energy. So you can think of this is the energy landscape. And you want to find this minimum over quantum models of classical spin models, okay? So in this case, this is the ground state energy. So what we do using similar approaches is like, we do outer approximations to the quantum, the physical realization. Remember before I was approximating quantum correlation from the outside, now I'm doing the same. I'm approximating quantum models or classical models from the outside. So if I minimize this function over the outer set, you will get either the solution or a lower bound to the solution because you are minimizing over a larger set. Okay, so I'm now going a bit fast, I'm sorry for that. But you should understand that we can adapt these techniques to find.
One question. So here you assume everything is done at the level of probability distributions. Yes, so, or?
Well, okay, now you will see. So what happens is that the techniques we are given, okay, so you can also think again as this as an expectation value. Okay, and then probabilities and all our machinery. I mean, I don't have time to tell you about this, okay, but the machinery we introduced for quantum correlations is actually a machinery for polynomial optimization. And this is a polynomial of some variables. And you can get outer approximation. Actually, we found out that what we were doing was the quantum analog of some techniques that were already existing in the classical regime, also for polynomial optimization, relaxations, okay? But the interesting thing is that these methods give you lower bounds in the case of ground state energy. So I think they might have some use in some problems.
Should I think of it as like this branch and bound method?
Okay, branch and bound, very good. Okay, yes. So what is the branch and bound? So people using classical, well, yes. So we are not the first doing this. Okay, so what happens? We do the following. So what I'm telling you is that these outer approximations to the relevant set gives you lower bounds. Okay, and a variational method or a quantum device gives you an upper bound. What happens in the case of classical? So what we did, we were testing this idea on classical systems. For classical systems, you can use, if you have a method to, there are ways of using a lower bound and an upper bound to improve them in this branch and bound method. Okay, so we also use these ideas. We made some variations over some of the methods. So basically what you do, you run a variational method, you get an upper bound, you run this relaxation, get a lower bound, and then from this knowledge, you keep improving, and then you close the gap. So you can really determine the ground state. Okay, so even if this doesn't happen, because some problems will be hard, at least you will have, even if you stop here and you don't improve the bounds, well, at least you will have some control about the quality. Okay, it will never happen something like this and this. Okay, you have some control about what's going on.
How do you obtain the lower bound? So the outer parameters.
So I don't have time. Okay, but this is what you do. Okay, so a ground state problem is a minimization over a space of physical parameters. The technique I told you for quantum correlations, it's basically a more general technique in which you have outer relaxations to a physically relevant set. I mean, it cannot be any physical relevant set, but for some relevant sets that are described through polynomial functions, you can find outer approximations. So instead of solving the original problem over this set, you solve it over the outer approximation, and this happens to be easier. Okay, then you know that this, I mean, if you run this problem over the set gamma 2, the problem will give you this, which is a lower bound to the minimum. Okay, I mean, here, if you run it over this set, you will get this. Okay, then you will solve the problem. But in general, you know that you have a lower bound.
Is it guaranteed for me that you will get? I mean,
you converge asymptotically. You converge, but what you need here, in principle, is infinite set. So it's asymptotically converging. Yes. Okay, so what we did this for classical systems, and there were also some previous works doing that. Okay, so for instance, we also used this. We were playing with the D-wave machine. Okay, so okay, look, sorry, I forgot something important. These methods, I mean, scalability is an issue. Okay, so we could go up to system of 35 times 35s. I mean, we cannot compete with Monte Carlo.